Good morning. We're going to start the meeting today. I have an announcement to make. Before, the dinner of the Congress is going to be held tonight, and it will be held in the hotel, Gilo Hotel. The people that has room there won't have to pay, but everybody else will have to pay. So, sorry. I don't know. According to the menu, as I understand. 7:30. Okay. Well, we start. We have today, we are honored to have the Dr. Camilo Rios. He had his bachelor in chemistry in UNAM, and then his PhD in pharmacia in CIVESTAP in Mexico City. And he's the head of the neurochemistry department in the National Institute of Neurology and Neurosurgery. It's something that doesn't seem to physics, new materials to regenerate spinal cord. But the main thing is that among the collaborations that he has is with us, the Department of Physics of the Universidad Autónoma Metropolitana. So he interacts with all kind of people, even physicists. Okay, without more introduction, I will allow you to let you, yes, over there, thank you.
Good morning to everybody. I want to thank Dr. Juan Morales and Dr. Olayo for their kind invitation to this meeting. It's a very prestigious and fine meeting, as I know. And, well, as Dr. Olayo said, I am a little bit far from physics, but also you are also far from neural sciences. So I am going to try to make you understand some basic issues on this subject, particularly subjects related to the regeneration of the central nervous system as a first stage in this talk. And then I am going to advance to more recent developments in the field of spinal cord injury and how to repair spinal cord injury using new materials, particularly polymer materials. So this is the numeralia about spinal cord injury. As you know, even Superman can get injured from the spinal cord. I'm talking about the actor Christopher Reeve, who suffered spinal cord trauma at the cervical level. So about 10,000 new patients are injured every year only in USA. It produces that about 250,000 patients are in every time suffering from the consequences of spinal cord injury. This is a very expensive disease because it affects mostly to patients between 16 or 18 and 30 years old as the result of the activities of these young people. 55% of the patients are coming from this age group. So they are patients with all the life in front of them. They are productive young people. Most of them are men, and nearly 40% of patients came from car accidents. About 25% of those people receive this spinal cord injury by violence acts, and the rest are coming from sports and work accidents. This is can be variable depending on the different countries. You know, for example, in Canada, there is a lot of accidents by the sports, by the snow sports or winter sports, and they have a higher proportion of accidents coming from sports. So, what happens if you receive a trauma in, for example, this level of the neck? If you receive a strong trauma here, you lose the function of this spinal cord, of this neural tissue, from this level to the bottom. So, if you receive a trauma in the thorax, you will lose the function, their nervous function, from this level and to the bottom. So, if, as in the case of Christopher Reeve, he received trauma in the neck after jumping with a horse. So he was paralyzed from all the four extremities because the trauma in that case was in the upper level of the spinal cord. So you can see here that the problem is that the spinal cord is like a tube, and if you cut by a trauma in the different levels, then the communication between the brain and the rest of the body is interrupted. So this is the main problem with spinal cord injury. Well, let's move about the basics of central nervous system, and I wonder if some of you perhaps know that nervous system is divided into central nervous system and peripheral nervous system. So central nervous system is composed by the brain, or the encephalon, and spinal cord. There are several differences between the organization of central nervous system and peripheral nervous system. One is the cellular components of these two different parts of this nervous system. In the case of the central nervous system, the the cell that is responsible for the functions is, of course, the neuron, as it is the same in the peripheral nervous system. However, the difference is that the myelination process, which is the covering of these, let's say, wires from brain into that come from the brain into the different organs, is made by a different type of cell, that is the oligodendrocyte cell. In the case of the peripheral nervous system, this is achieved the same function, the covering of the axon, of the prolongations of the neuron is done by the Schwann cells. So this is a major difference between the peripheral nervous system and the central nervous system, and it's one of the main reasons because central nervous system is so difficult to repair. Because in the case of the cellular components, these oligodendrocytes is able to myelinate. Here's a scheme of the neuron. So you can see how it's composed, this cell. So it's a soma where it is located, the nucleus of the cell. Then a very large prolongation of these cells named axon. And this axon is covered by these proteins that form a sheet surrounding the axon. These sheets are made principally by myelin. So the process, the whole process of this is myelinization of the axon. So it is like an insulator for the cell to conduct the electrical current from the soma to the terminal here. So in the central nervous system, this myelin sheet is produced by oligodendrocytes. One oligodendrocyte cell is able to myelinate many neurons. So if one of these cells, these oligodendrocyte cells, is destroyed or dead, then many of the neurons are affected because they can lose their myelin sheet. So this is the case of the central nervous system. In the case of the peripheral nervous system, the relationship is 1-to-1. It means that a single Schwann cell is able to myelinate a single axon. So if one Schwann cell is lost, then only one neuron is affected. In the case of the central nervous system, many of the cells are affected by this demyelinization process. So this is one of the difference between peripheral nervous system and central nervous system. So what are the challenges to repair central nervous system and specifically spinal cord? One is that central nervous system are unable to proliferate in the adult life. So you can't produce, for example, skin cells or muscle cells along all your life. But in the case of the neurons, they are very limited capacity to replicate, to produce a new neuron, a new cell. So this is a problem with central nervous system neurons. They don't proliferate. A second problem is that after spinal cord injury, there is a series of processes that inhibit the regeneration of the same cell, because there are some markers, molecular markers that indicate to the cell that it is not needed to regenerate the axon because it is an adult subject. In the case of the developing central nervous system, for example, a child of 2 years old, they have these inhibitory growth molecules down-regulated because they are growing their central nervous systems. So this is stopped in the adult life, and then when you receive a trauma in the spinal cord, these grow in inhibitory molecules are going up to stop any process to regenerate central nervous system. So, what are some other problems? The imbalance, for example, in neurotransmitters that can even expand the lesion. The initial volume of the lesion is relatively small, but after a series of autodestructive processes, this original lesion, the primary lesion due to the trauma, are expanded into different nearly areas of the spinal cord. So it's like a neurodegenerative process started by the trauma. So this is one of the preparations for microscopy we use to evaluate spinal cord injury and the repair of spinal cord. I am going to give you a tip to understand these microphotographs, and it is all you see here in blue is neuronal healthy tissue. So if you see blue, you are looking at central nervous system cells, I mean neurons, and the blue color comes from the staining of the myelin, of this sheet around the axon. So if you see here blue, you see healthy tissue. This is a rat, spinal cord from a rat, and you can see here how it's the cytoarchitecture of this spinal cord. In the right side, we can see 8 weeks after a single trauma to this spinal cord of the rat. You can see here how most of the tissue of the neurons have disappeared. So you see here a hole with no tissue, and many small cysts here showing that the disappearance of the cells are coming from the epicenter of the lesion toward both sides of the spinal cord. So that is what happens with the spine, with a moderate spinal cord trauma. So what are those events that led to reduced ability of the spinal cord to repair himself or itself? That the main processes that take place after spinal cord injury are here represented in a time scale after injury. So injury is here at time 0, and then the several post-traumatic events that led to this injury to be expanded. So in the acute phase, namely the first hours after trauma and let's say 2 or 3 days after trauma, you can see the arrival from the blood, the arrival of several cells that respond to tissue damage everywhere in the body. They are the inflammatory response cells. They are their function is to arrive to the site of the injury and to try to reduce the quantity of cells damaged. This is the rationale for this inflammatory response, to reduce the amount of cells damaged. Then this is the acute phase. The oligodendrocyte cell is dead, is going to death by different processes, apoptosis or necrosis. And then as oligodendrocytes are lost, then demyelinization process takes place, as I explained in the previous slides. So the initial axonal degeneration takes place in this acute phase, and there are many local neurons that going to be disappeared from the tissue. And then at the subacute, let's say several weeks to months after trauma, some other processes take place. For example, the glial scar formation. This is a scar in the central nervous system. The scar is formed mainly by these other cells, the glial cells. And then some other distant processes of neurodegeneration. That it means that the neurodegeneration is being expanded to the neighborhood very rapidly after the chronic process. So this is one of the main problems with spinal cord repair. If you look at the normal wound healing in, for example, skin or muscles, you see that this initial phase, these are the different stages in time intervals I talked before, and you can see here how the phase 1, that it's related to the inflammation period, is self-contained in the case of the normal wound healing, for example, as I said, in skin or muscle. It is terminated after, let's say, day 4 after injury. This is what is happening in wound healing in skin, for example. Then, after this phase 1 of inflammation mediated by these cells, the macrophages cells coming from the blood, After this process is finished, then a second phase is taking place from day 4, let's say, until day 10, approximately. And in this phase, there is a proliferation of the cells. From, for example, in the case of the skin, the formation of a new skin to cover the lesion. And then, after this process is still taking place, then a phase 3 starts, which is the remodeling of the tissue, meaning that all these new cells are going to establish patterns of connection with the other cells, with the old cells, that they're not wounded cells. Then these 3 processes take place one after the other. But in the case of spinal cord injury, the healing process is completely different. For example, the phase 1, meaning the inflammation process, is still present several months after spinal cord injury in the cells of the spinal cord. So this inflammation, this phase 1, is never-ending phase. Then delaying the phase 2, because the mediators of inflammation, the molecules that call for these processes to continue, are still present for a very long time. And then phase 2, proliferation, is reduced because the presence of these phase 1 mediators, molecules. And then practically no phase 3 is taking place because this inflammation prevents the occurrence of both proliferation phase and remodeling phase. So it is what means that it is very important to prevent these inflammation processes before you can repair spinal cord injury. So several strategies have been taking place to start with the good repair of the spinal cord. One is to transplant cells to initiate a new by the means of grafts to prevent, to replace the cells dead after trauma. But I am going right now to be focused on a different kind of strategy, and it is the use of polymer or material scaffolds to induce the regeneration of the spinal cord. This is a very recent paper published in Neurosurgery with the first human implantation case for a polymer scaffold for the treatment of acute spinal cord injury. This is a paper published this year by the group of Dr. Theodore at Phoenix University. He is one of the main researchers in the field of spinal cord trauma and repair, and he's working at the Barrow Institute in Phoenix. So what they did was to put this piece of polymer. It's a biodegradable material, meaning that it can be cut in small pieces and these small pieces are being metabolized by the tissue itself. So this kind of polylactic or glycolic acid, which is conjugated with lysine, with polylysine, was put here in the spinal cord of one patient to induce the repair of spinal cord. So this is how the implant looks like. This is a coin for you to see how big or how small is this implant. And then if you look at the microscopy, electron microscopy, you can see that the structural appearance of the polymer material is a very porous material. A very porous material, and it was implanted here. The patient is improved their walking after a spinal cord injury in a very interesting and promising way, because he was with the Asia scale of A, meaning that he couldn't move their legs, and he couldn't control the urination process. And after 6 months, he is now walking with the assistance of one chair, and he is now with a bit of control of the bladder function. So it's a promising result, and this is the first case. So we have been working with this parole-derived material. It is there are some reports in the literature showing that these materials, parole-derived materials, are good for the interaction with neurons, increasing proliferation in cell culture plates. This is in vitro experiments. In vivo, they reduce inflammatory gliosis around the implant, and they have good tolerance of the host tissue. There are some reports showing that these materials could be interesting for use in spinal cord injury. So we started this study with this material in 2008. We published this paper in Journal of Material Science, Materials in Medicine, trying to use this polypyrrole-derived material to implant into the spinal cord of rats after a lesion. So these materials are produced by a plasma reactor. The monomer is introduced into this chamber to polymerizate, to initiate the polymerization by the glowing discharges of electricity, and then the polypyrrole, for example, the polypyrrole produced in that way is recovered. You can see here, compared again with the coin, a Mexican coin, and you can see how it looks like this material after being compressed by 9 tons of pressure to form a thin film of material. In this way, we were able to introduce this small film into the spinal cord after transection. Transection is a surgery operation to the rat, which leads to the separation of the spinal cord in 2 pieces by a knife. So, here is the material, and this is the molecule, the parole molecule, and then when it is subject of polymerization process, it forms these kind of structures, or even this other kind of structure, a more cross-linked polymer. And of course, it was characterized by chemical composition, for example, the nitrogen and carbon bonds and the carbon-carbon bonds were characterized by infrared spectroscopy. We also use electron microscopy to see how they look at the nanoscale. And these are the materials studied by electron microscopy. And you can see one of the polymers was this polypyrrole. It's this molecule, polypyrrole. This is a copolymer of polypyrrole and polyethylene glycol. This is the structure, and this is polypyrrole doped with iodine. Iodine is used here to dope the polypyrrole during the synthetic process of the polymer. So this is the electric conductivity at different moisture, percent of moisture in the environment, and you can see these are sieverts per centimeter, and you can see how the conductivity depends on the moisture of the relative moisture of the measurement, and after this amount, 70% of moisture, the material became very conductive. So we implanted this material in the spinal cord of rats. These kind of rats are long Evans rats. They receive a lesion at this level, in thoracic level 9, the ninth vertebra of the spinal cord, and they were cut the entire spinal cord with the use of a knife, a surgical knife. So this is a model of complete transection of the spinal cord. This was our first approach because we have the thin film, and we put this thin film after this the perform of this cut of the spinal cord. So several groups were formed, a control group receiving only spinal cord injury, a group with spinal cord injury and polypyrrole implant, a group with spinal cord injury and polypyrrole doped with iodine, and spinal cord injury and plus the implant of polypyrrole and polyethylene glycol copolymer. This is the tissue response of the implant. You can see here, this is 8 weeks after the lesion, after the transection of the spinal cord. You can see here the spinal cord looks like a tube, as I said, and how in the site of the transection, the spinal cord has lost almost all of the neuronal material, and you can see here the implant is a brownish material, and how this implant is being let's say incorporated by neural tissue. So again, as I gave you the tip before, all in blue are neurons or myelin. So you can see here, this is the polypyrrole doped with iodine. You can see how the neuronal material, the myelin, is getting into, look like it's getting into the material, the polymer material. So even in some cases, the blue material, meaning that the axons of the neurons are going along a fiber of the polymer. For example, in this case, there are several fibers here of the polymeric material, and also several fibers of probably new prolongations of the neural tissue. So, as I said before, macrophages and inflammatory response is one of the main problems to prevent spinal cord injury repair. And in this microphotograph, you can see a specific marker for macrophages. The marker for macrophages are inflammatory cells that infiltrate neural tissue from the blood. And you can see the mark for macrophages in brown, and again the myelin is stained in blue. So this is the control rat 8 weeks after trauma, after spinal cord lesion, and you see a lot of brown material, meaning that there is a lot of macrophages even 8 weeks after spinal cord injury. And when polypyrrole is implanted in the spinal cord, you can see also some brown material, meaning there are still macrophages, but there is a lot of blue in between, you can see here, meaning that this is healthy tissue that has not been infiltrated by macrophages. So after this experiment, we suspected that polypyrrole is being anti-inflammatory to the tissue. So if you remember how the repair process is working, So we are acting on the inflammatory phase 1 process with this polymer. So we evaluated how good the motor behavior of the rats is being done after the transection, and we use to evaluate this, we use this scale, the BBB scale. This scale is rating the rat motor activity of the posterior legs, or posterior limbs, as 0 in the absence of movement, like this rat here, and 21 to the normal walking of a rat, the coordinated movement of the limbs. And you can see here how the recovery of the rat occurs after spinal cord transection. This is 0, remember, is no movement, and 21 up there is full recovery. And you can see here how after 8 weeks, rats recover very little, about nearly 2 points in this scale. But in the case of the polypyrrole doped with iodine, the rats became very successful in recovering the walking by 8 weeks, until almost the double of the recovery of control rats. So this is a measurement of a spare spinal cord tissue, meaning that this is the percentage of tissue that remains healthy after 8 weeks of the spinal cord injury. And you can see here the control, about 10–12% of their 100% is the tissue from a control rat without spinal cord injury. And you can see almost the double or even more of the tissue is recovered by polypyrrole doped with iodine, and also with the copolymer polypyrrole polyethylene glycol. Oh, sorry, I don't know. Okay. However, this is a very artificial or artifactual model for spinal cord injury, because very few patients receive a transection, a complete transection of spinal cord. Most of them receive a contusion in the spinal cord. So we move to a different model of spinal cord injury. This is achieved by a weight, small metal weight that is being released directly into the spinal cord. This produces a trauma that is very well controlled, because it is connected to computer systems that make the record for the speed and the deformation of the spinal cord after this trauma. So, in this model, of course, there is no separation between the two extremes from the two extremes of the spinal cord, as for example in the transection model. So you need to inject the polymer particles with a syringe directly into the spinal cord injury epicenter. So that's what we did. This paper is now in press in the Spine Journal, one of the major journals in the spinal cord science. And this is the kind of material we injected, are particles, small particles of maybe 100 nanometers, 200 maybe, 200 nanometers of diameter. And this is how these particles look like after being injected into tissue. Again, the blue color are the different myelinase axons, and the brownish material is the polymer particles. So you can see how most of the particles are surrounded by healthy neuronal tissue. Again, this is also 8 weeks after the injection of the material. So this is the infrared spectrum of the particles. And for the evaluation of the success of this injection, we use nuclear magnetic resonance images in a commercial 3 Tesla equipment from our hospital, and we were able to locate with these images the site of the lesion. This is the control rat receiving no particles of the polymers, and you can see here in the lower lane the images from several rats with receiving the trauma, and then 48 hours later the injection of the spinal cord, the polymer particles. So in this case we were able to measure the 2 physical parameters that are available in the nuclear magnetic resonance images, and they are the apparent diffusion coefficient and the fractional anisotropy. They are measurements or values that give us information about how the order of the spinal cord is being in the tissue. For example, in the case of the fractional anisotropy, a fractional anisotropy close to 1 indicate that water molecules are moving preferentially in one direction. And in the case of this fractional anisotropy, 0 means that there is a movement in a sphere, showing no preference for any direction. So this is before spinal cord injury and then after the spinal cord injury. You can see here how after several weeks of the spinal cord injury, rats receiving the polymer particles recover better this fractional anisotropy. In the case of apparent diffusion coefficient, it's the opposite as in the case of fractional anisotropy, but again we found a better performance in these parameters in the animals implanted. These are how these two parameters measured by nuclear magnetic resonance images are correlated with the motor scale, for example, and with the amount of tissue measured, spare tissue measured by histology. And we also have started with experiments with monkeys as a previous step to go to the human beings. And this is an experiment with rhesus monkeys. They receive a transection lesion, and then the injection of particles. This was a thin film implant, and what we observed was that in the case of the control monkey, he received no implant, and the fractional anisotropy is going down, meaning that the water can move in every direction without a preference. But in the case of the monkey implanted with polymer, this is the value before lesion, and then goes down to this value, but then after 1 and 2 and 1 week, 1 month and 2 months, the values of this parameter going up, on the contrary, in the control went down. So this is the image. The left-hand image is at the moment of the transection. You can see here how it's the cut of the spinal cord. And 2 months after that lesion, you can see that even more space between the two endings of the spinal cord. But in the case of the monkey implanted with the polymer, you can see here 1 day after the lesion, you can see the separation. But 2 months after the lesion, you can see here as some kind of bridge between this extreme of the spinal cord and the other. So, and you can see here how some material, spinal cord tissue is being lost after in the control animal after the spinal cord injury, but you can't see this effect in the implanted monkey. So, in these 2 monkeys, we were able to measure the inflammatory messengers in blood to test the hypothesis that this material can be anti-inflammatory. And what we found was that all of the inflammatory markers, for example, interleukin-2, interleukin-6, tumoral necrosis factor alpha, and some others, all of them are being decreased 24 hours after implant. This is the control monkey, and this is the monkey implanted with the polymer. And you can see how in all the markers and at all times there is a decrease in the inflammatory response in the blood of these monkeys. You can see in black it is the values of the control monkey. So, thank you very much.
We have time for 1 or 2 questions. Yes, please.
what happens if the injury doesn't affect all the cross-section of the spinal cord, but just a small split piece, an edge or something? Do you lose motion partially, or what happens with the patient?
Yeah, well, you can, even with a severe lesion, you can still move partially some of your limbs, meaning that the lesion needs to be very severe to lost every of your functions. But for example, the walking is a very difficult function because it relies on many muscles in the legs. So as it is a difficult, complex process, walking, so you need a lot of innervation from spinal cord to the muscles to move. So it's the complexity of the movement what is the problem. So you can still move some of the muscles, but you need coordination of the different muscles to move.
Very nice talk.
Thank you.
Quick question about, I guess, the transection experiments and the role of the PEG in the polypyrrole particles. Have you tried either using just PEG as a thin film, or what is, I guess, the difference in the role of the PEG versus the iodine-doped particles?
As I said, most of the lesions in human beings are due to trauma, meaning that transection is not a good model for what is happening with the human beings. So we, after doing several experiments with transection model, we moved to the trauma model. So in the case of the trauma, you have a little space in the spinal cord to receive a thin film, because you have to open again and remove all the material after the spinal cord transection, and then even cut again to implant the thin film. So it is a matter of how difficult it could be this to translate into human beings. That's why we moved to the trauma model.
Yes.
In the case of the rats, you introduced a scale extending from 0 to 20 somewhat to characterize the abilities to move. How can you calculate or determine these values in a controlled way? So
then, you are asking about how we measure the recovery of the rats?
Exactly. So you introduced a scale, and
it's a scoring. It's a scale. It's dependent on the observer, but for example, 0 means no movement.
Yeah.
1 of this scale means that the rat can move a little bit the one of the legs. And 2, it means that can move both small displacements of both limbs, and so on. So if you got a coordinated walk, then you have maybe 15 in the scale. So it's an improvement scaling.
Sure, but you just look onto the rats and determine the value, or is there some? You are just looking onto the rats. Look on the rats and then you determine the scale, or is there maybe an objective measurement by some apparatus to determine it?
No, it's a visual observation, and we can record with the camera.
And does the observer know whether it is a control rat or not?
No entendí.
to answer that. You have observer and you score the rat according to the movement, and the observer doesn't know which rat is which
it's
one.
a blind.
So it's a blind observation, and so the after they score it. They know after, I mean, they score them for 2 months, and then the average are taken afterwards.
Yeah, it's a blind design. So the observer is not aware about the treatments.
I think this is very essential for such.
Yeah, that's right.
observations.
That's right. In every case, we take that care to prevent.
Even most of the time, there are 3 scorers. So different people see them in order to be sure of what you see. Anyhow, you are not allowed to convoke them. So if they don't want to walk that day, it's a 0, and you have to put it there.
Okay. Okay.
In this situation, is there a biological function for inflammation, or is it something that we can get rid of without any bad consequence? Or
No, inflammation is a physiopathological response, so it gets an important function for the body, and the function is to isolate the damage into a very limited space in order to prevent the expansion of the damage. So this is the normal idea of this inflammation. But in the case of central nervous system, the problem is that the inflammation is occurring within several walls of bone. You know, the bones are surrounding all central nervous system. So inflammations can even damage more than the initial damage, the primary lesion.
What kind of lesion did the patient
Trauma.
Yes, what kind of lesion had this patient?
As far as I read the paper, because it's very recent, it was a car accident.
A car accident?
And then a displacement of the vertebra.
Okay.
So it's a compression lesion.
And
Compression.
The results?
And the results seems to be good, but it is still just one patient.
Okay.
We thank Professor.
Thank you.
Okay, please do not forget that tonight is the conference dinner at the Gilo Hotel at 8:30 p.m.